In this video, you will learn the complete design and detailing of reinforced concrete ramp using Etabs. The scenario is given as compressive strength of concrete 5 KSI, yield strength of steel is 60 KSI, column size as 8 by 20, vehicular load to be use UBC 97. The dimensions and the elevation of the ramp is given. So checking whether the ramp is one way or two way. The dimension shows slab is one way as follows. The width of the ramp is 10 feet and the length between the beams at the ends is 42 feet. So the slab is one way since the ratio is greater than 2. The strips will be drawn on the longer side, or it's a choice whether not to draw the strip and use the moment for the design. So we will be using moments for the design for time being. The number of stories is 1 and the difference between start point and the end point is 4 feet. Spacing of grids in X and X is not uniform, so we need to use the custom grid spacing. The spacing between grid A and B is 5, B and C is 9, C, D, and the rest will be as given situation. The spacings are now set. So using the y-axis grid data, which is only 10 feet one direction and the rest are to be deleted. So press OK. You may turn off the 3D plan view. Since we will be drawing columns which requires plan view. So first we will be defining the material properties. The material strength for concrete was given as 5 KSI or 5000 PSI. Adding the material property for steel, name it as G60 deformed so that it's easy to identify which material we defined. Now we will be defining the section properties for the beams and columns. You may delete the properties which are useless or will not be used, such as the steel section which has predefined. So now we will be defining our required sections which were given in this situation. The column, it's all depending on your requirements whether to take the width and the depth of the column as 8 or 20 or 20 or 8. The property modifiers of the column is 0.7 according to ACI code to incorporate the crack moment of inertia. Select the steel which you defined for the column. Click on reinforcement to be designed so that the input reinforcement does not plays any role which was predefined. Now we need to select or define the ramp beam. (8 by 24). Reinforcement section, it is to be designed as beam. Property modifiers for the beam using ACI code as 0.35 to incorporate the crack moment of inertia. And if you don't want any torsion in the beam and slab to take all the torsion, take torsion constant as nominal amount, that is 0.001 or 0001. Slab sections, add new property for the ramp slab, or in other words, it's the base slab of the ramp. The thickness was given already as 7 inches. In order to understand the difference between shell thin and shell membrane, you need to click on the video whose link is given in the description. Right now I am assuming we have gone through that, so I am selecting shell thin. According to ACI code, the crack moment of inertia is 0.25 times of the effective moment of inertia. So we incorporate the property modifier, click on OK. Delete the properties which are unnecessarily defined. Let's define the load patterns. Dead and live is already defined. Super dead load is to be included in super dead. Now let's model the ramp. First we will be drawing the columns in the plan view. To draw between the grid intersections, just drag the cursor simply, and the centroid will be placed on the grid intersection. So we will be adding the ramp beam at the topmost corner where the ramp extends upwards, and we will be requiring another beam at the down corner. For that we will have to go to the base. In 3D view we will be drawing the inclined beams for the ramp. First we need to make the supports of the columns as fixed, which is a more realistic case. Now taking the top supports of the column as fixed, since the structure would be in continuity with the rest of the building. So we haven't modeled the whole building, just the ramp part. So taking the bottom and the top as fixed. So you see I forgot this column. You can always select the joint and assign restraints to the joint. So now we are done with assigning restraints. We will draw the inclined beam now. Starting from the top beam, to the end. Similarly, so now you see the beam is not joined with the columns. So we need to break the columns at the point where the beam has to have a joint with the columns. Go to edit frames and divide frame option. Break at intersection with selected frame and joints. So now you see a joint is automatically formed between the columns and the beams. Similarly for the other side. We need to draw the ramp slab. Using the joints as the support for beam, press enter to complete drawing the slab. So I am drawing the slab between the joint of column and beam using the snap options from the draw tab. If you haven't turned on the snap options, you may always turn on from the draw tab and click on snap options. So now we are done with drawing the ramp, or you can say we are done with modeling of the ramp in a 3 dimension. You may have to carefully see whether the joints are properly restrained. Now we have to draw or match the slab. So let's take the meshing as 2 feet or 24 inches. Usually a maximum size of meshing recommended is 3 feet for accuracy. For higher accuracy you can always select a lower meshing size, but it will slow down the analysis of the model. So for in spite of 3 feet I am taking as 2 feet since it's not a large structure and will not take much time to run. Using the none property beam I will match the slab. First drawing the beams. So now the meshing or the beams which will help us to match the slab are drawn. Select the slabs as well as the beams which will be meshing the slab. So go to edit shells, divide at selected intersection and frame objects. So now the slab is meshed. Now select the beams which you draw using the property none. Now delete these beams. So now we have a meshed slab in the longer direction. Now assign the loads to the slabs. Live load from UBC 97 for the garages and general warehouse. per storage is 100 bsf, and the super dead load was given as. In order to rectify the load, right click on a slab panel. You can always check the loads assigned in the undeformed state. Now go to load combinations and add default design combinations. So I'm using the FEM method. You may always check for the cover already specified. Since we are taking the cover as 3/4 inches, so I'm specifying it. For direction 2, which would be distribution reinforcement, you can also take the cover as 1 inches, subtracting the diameter of the main bar. So check the model with minimum tolerance so that no meshing error or the shell overlap error occurs. The model has been checked and no error messages were generated. So now run the model. It will prompt a save option. After saving, it will run the model. Now we need to check for the maximum moments in absolute terms. So we are concerned with absolute terms, we will have to look in the minimum as well. Let's select the load combination 1, shell stresses. Since we are required in slab, maximum stress, absolute maximum. So the maximum positive value is 24.74 for this case, and using minimum combination case is still 24. So using the second combination, the maximum value is 43, and for minimum is 0.6. So the maximum positive value of moment we are getting is 45 kip feet. So we need to calculate the rebar for the maximum positive moment, that is bottom steel. Since the positive reinforcement is the bottom steel, which is calculated as shown. Now our concern is to look for the absolute minimum value, that is negative maximum moment, using both the combinations. So the maximum negative moment value we are getting was 45.27 kip feet, which will be used for designing the reinforcement in the shorter direction. The maximum negative reinforcement will be the top reinforcement. Since the top supports provide resistance to the negative reinforcement or the negative moment, the calculation for negative reinforcement or the top reinforcement is shown. Moment divided by 4 times effective depth. Now we will be detailing the reinforcement in the AutoCAD drawing. The shorter direction reinforcement is the main reinforcement since it is a one-way slab. So the top reinforcement and the bottom reinforcement for the shorter direction was found by Etabs using the maximum positive and negative moments, which was number 7 at 4 in center to center in top as well as bottom. For distribution reinforcement calculation, we need to use the minimum percentage of steel. Effective depth is calculated by subtracting the cover. Let's say 9-inch center to center for number 3 bars of distribution reinforcement is to be provided. The distribution reinforcement is in long direction, number 3 at 9 inches center to center. For complete Etabs tutorial, visit the channel and go to playlist name Etabs. Please subscribe for much more to come.